In this presentation, I will explain how transformers work, their basic function, demonstrate transformer math, and relate their function to X-ray generation. For more advanced transformer concepts like transformer cores and autotransformers, refer to Part 2 of my transformer lessons. If you don't understand what AC power is, consult my lesson on AC power. Before we begin, we must start with an explanation of basic transformer anatomy, so we are all on the same page regarding terminology. To construct a transformer, we start with a coil of wire. Now, we place a second coil of wire very close to the first coil. This second coil is electrically insulated from the first coil. Electricity cannot directly flow from one coil to the other. To the left of the first coil, we connect a power supply, in this case an AC generator. This coil is called the primary coil, the primary coil being the coil connected to the supply of power. To the right of the second coil is connected, in this case, a resistor. This coil is called the secondary coil, the secondary coil being connected to the device being powered, like a light bulb, a motor, or an X-ray tube, for example. All wires that transmit electricity have a magnetic field surrounding them. Also, if a magnetic field is moved relative to a wire or coil of wire, a current flow will be induced in that wire. A transformer consists of two coils near one another. Both are stationary. If the voltage in one wire is constantly fluctuating, the magnetic field around the wire will expand and collapse in time with the voltage. A characteristic of AC power generation is the voltage fluctuates during its generation. AC electricity is normally used to power transformers. DC power does not fluctuate, but is a constant voltage from the time the power is started to the time the power is turned off. So DC power cannot power a transformer without extensive modification to make it fluctuate. The primary use of a transformer is to change voltage in a circuit, either up or down. If a transformer has more coils in the secondary than the primary, it will increase the voltage in proportion to the ratio of coils. This is how an X-ray machine can have an input voltage of 120 volts and then provide a voltage of 70,000 volts for powering the X-ray tube. On the other hand, if a transformer has more coils of wire in the primary than the secondary, it will decrease the voltage in proportion to the ratio of coils. This transformer is called a step-down transformer. Step-down transformers are often found in cell phone chargers that convert 120 volts of line voltage to the 5 volts necessary to power your cell phone. Here is a basic transformer circuit. The primary is on the left, the secondary on the right. A transformer has no moving parts. Movement of the magnetic field is caused by the AC fluctuation of voltage on the primary side of the transformer. See, as the voltage increases on the primary side of the transformer, the magnetic field expands, moving across the secondary coils, inducing a current flow in the secondary. Note that the north pole is located at the top of the primary coil. The magnetic field then collapses, and the current flow in the secondary is reduced back to zero. As the reverse pulse of power is generated in the primary coil, the polarity in the coil switches to the south pole at the top of the coil. As the field expands and collapses, it creates current flow in either direction, secondary side of the transformer. Let's repeat the animation with one modification. At the bottom of the screen, I've replaced the text with an oscilloscope display that will illustrate the AC waveform in step with the magnetic field's movement. Let's repeat this animation one more time just for clarity's sake. The main purpose of a step-up transformer is to change a low voltage to a higher voltage. The high voltage transformer in an X-ray machine transforms 120 volts of input power to 70 or more kilovolts applied to the X-ray tube. A step-up transformer has more coils in the secondary than in the primary. Let's apply 120 volts AC to the primary of this transformer. There are 8 coils in the primary and 16 in the secondary. There is an equation that applies to this situation. Voltage in the primary is proportional to the coils or turns in the primary, and the voltage in the secondary is proportional to the coils or turns in the secondary. Just remember that the primary and secondary variables line up above and below the numerator line. Next, we substitute numbers for the variable names, solve for x, and when we do the math, we find our new voltage is 240 volts. Actually, the number of coils is not important, but rather the ratio of coils, primary to secondary, is the governing factor. The law of conservation of energy states that energy cannot be created or destroyed, and this rule applies to transformers as well. If voltage increases, something must decrease, and in this case of the step-up transformer, it is amperage. Let's apply 10 amps AC to the primary of this transformer. Again, there are 8 coils in the primary and 16 in the secondary. This equation looks like the previous equation with one important difference. Amperage in the primary is inversely proportional to the coils or turns in the primary, and the amperage in the secondary is inversely proportional to the coils or turns in the secondary. Just remember that the primary and secondary variables do not line up above and below the numerator line. Now we substitute numbers for the variable names, solve for x, and when we do the math, we find the new amperage is 5 amps. Again, the number of coils is not important, but rather the ratio of coils, primary to secondary, are what makes the difference. The main purpose of a step-down transformer is to decrease voltage. Your cell phone operates at about 5 volts. Inside your charger is a transformer that decreases 120 volts of the wall socket to 5 volts necessary to charge your cell phone batteries. Let's apply 120 volts AC to the primary of this transformer. There are 16 coils in the primary of this transformer, and the secondary side we count 8 coils. The transformer is different from the previous example. It has more coils in the primary side. We use the same equation that we used in the previous example. Voltage and the number of coils are proportional to each other. Next, we substitute the variable numbers for the variable names, solve for x, and when we do the math, we find the new voltage is 60 volts, exactly half the input voltage. I won't bother providing an amperage example. Hopefully it is obvious that if voltage decreases by a factor of 2, amperage will increase by the same amount. To summarize, transformers require a fluctuating power source to operate. AC power meets that requirement. Under certain circumstances, DC power can be made to fluctuate, but it requires fast mechanical switches or complicated circuitry. The transformer consists of 2 coils in close proximity to one another, but electrically insulated from each other. The primary coil produces an ever-expanding and collapsing magnetic field that induces a current flow in the secondary. The most common use of a transformer is to match voltage to a particular device or application. A step-up transformer has more coils in the secondary than the primary. The ratio of secondary to primary coils controls the amount of voltage increase the transformer provides. The laws of the universe apply to transformers, and if a voltage increases, the available amount of amperage decreases by a similar amount. A step-down transformer has more coils in the primary than the secondary. Its effect will be to decrease the voltage and increase the amount of amperage available to the circuit. Thank you for your attention. To learn more about transformers, refer to Part 2 of my transformer lessons.